Welcome to this video lecture on the topic dielectric boundary conditions. So first of all, what is boundary condition? In practical electromagnetic problems, it involves medium with different physical properties. So determination of electric field for such problems requires the knowledge of relations of field quantities at an interface between the two mediums. So the conditions that the field must satisfy at the interface of two different medium are referred to as boundary conditions. So for example, we can consider two different mediums. It may be a dielectric or conductor, or it is a free space. So in this case, we take two perfect dielectric materials. So medium 1 and medium 2 with different permittivities. So medium 1 has permittivity of epsilon 1 and medium 2 has permittivity of epsilon 2. So there are two different mediums. It may be glass or plastic, like this. So first, medium 1, we consider the field as E1 and medium 2 it is E2, and field entering the medium E1 can be undergo some refraction. So to derive these conditions, we are considering a closed loop and an cylindrical surface. So first we consider the closed loop, where we can express the electric field in terms of two quantities. One is tangential and another one is normal component. So the electric field is equal to sum of tangential component plus normal component. So where E1, E2 are tangential and normal components of electric field respectively. So for consider around a closed path, obtaining a conservative field, we are applying the conservative law of electric field, and we get this equation: E tangential component equal to E tan 1 2. So here the small contribution to the line integral by the normal component becomes negligible. So this states that the tangential components are continuous across the boundary. And in the next case, we consider D vector. So if the tangential electric field intensity is continuous across the boundary, then the tangential D vector, that is electric flux density, is discontinuous. So here, using the relation between D and E, we derive tangential component divided by permittivity equal to E tan 1. So this relation gives the discontinuous components across the boundary. So the boundary conditions on the normal components are found by applying the Gauss law to the cylindrical surface known as the pillbox. So the here we obtain d into del s minus d into del s equal to rho s into del s. So this is applied using the Gauss law, and we get dn1 equal to dn2, where the normal components are continuous across the boundary, and electric field is discontinuous. So here we are considering the refraction of vector d or e at the charge free dielectric interface. So here when it enters from medium 2 to medium 1, refraction occurs. So we can derive the formula using the uh, trigonometry. So we are considering tangential normal component of flux density, and we are equating to dn in 1 equal to dn2, where it is equivalent to d1 cos theta 1 equal to d2 cos theta 2. So from this we obtain the relation between flux density and permittivity values. And tan theta 1 divided by tan theta 2 equal to epsilon 1 by epsilon 2. So this gives the relation between incident and refractant angle, and the magnitude of D can be found using this relation, and also magnitude of E2 electric field intensity can be found. So we can have the assessment. First one, which component of the electric field intensity is continuous at the boundary? So the answer is tangential, because at the boundary the dielectric between two mediums are considered as dielectric. So the tangential components are always continuous. So second question, for a conservative field of which of the following equations holds good? So here the answer is A, that is integral of E dot dl equal to 0. That is, around a closed path the potential is 0, so that implies integral E dot dl vector is equal to 0. These are the references. Thank you for listening.